All right. Chemistry 3101. We're going to start chapter 7, which deals with alkyl halides, nucleophilic substitution, and elimination reactions. You can see it's a pretty long chapter. If you rifle down here, it's a total of what? 115 slides is what we have to go through. And I'm pretty sure that all of you have heard, echoes in your life about organic chemistry from friends who have taken the class before. And you might have heard the terms SN1, SN2, E1, and E2. Well, those four types of reactions are covered in this chapter. We're also going to be talking more about nucleophiles and electrophiles, and we'll talk about what are called substitution reactions that you see here in the title and elimination reactions. We're also going to talk about the halogens quite a bit, okay? Not so much fluorine. Fluorine's not really going to make that many appearances, but chlorine, bromine, and iodine will. And if you're wondering, well, why would fluorine not show up, but the other halogens show up? Like, what is special about these three? Well, if you think about their conjugate acids, right, if you compare HF versus HCl versus HBr versus HI, well, it turns out that those three are strong acids, whereas HF is not a strong acid. It's a dangerous acid, I'll give you that, but it is actually categorized as a weak acid. And so that's why their conjugate bases, the chloride ion, the bromide ion, and the iodide ion, that's why they're all what we call good leaving groups, okay? Whereas a fluoride ion is not a good leaving group. And so that's why we don't talk about fluorine a whole lot in this chapter. But like I said, chloride, bromide, and iodide show up just about Avogadro's number of times in this chapter. All right, so let's get to it. And let's talk a little bit about alkyl halides. So you guys know what an alkyl group is, right? We call an alkyl group an R group a lot of the time. And then for the halogens, we use the letter X to represent a halogen. There's no element X, but you can see down here, the X will mean chlorine, bromine, and iodine. And I explained why we don't talk about fluorine a whole lot. It's because fluorine, the fluoride ion is the conjugate base of a weak acid, whereas chloride, bromide, and iodide are all the conjugate bases of strong acids. So alkyl halides, it turns out, undergo what we call substitution and elimination reactions. So again, if you've heard any echoes about the class before you came in here, substitution, those would be things like SN1 and SN2 reactions. And then elimination, that would be things like an E1 or an E2 reaction. And we're going to probably get into those today. So an alkyl halide is one where we have the halogen attached to a carbon, and it says, what is the hybridization of each one of the carbons here? Well, you can see that somebody already went ahead and labeled them as sp3, sp2, and sp2. But which one represents an alkyl halide? Well, remember, an alkyl group is something like an ethyl or a propyl or something like that. And so it's going to be attached to an sp3 hybridized carbon. So something where the hybridization is sp3 of your carbon and it's attached to a halogen. So we'll say sp3 hybridized, sp3 hybridized carbon attached to a halogen. That counts as an alkyl halide. This would be an aryl halide, and this would be a vinyl halide, and we're not really going to talk about either of those a whole lot in this class. So it turns out that when you have an alkyl halide, so your halogen attached to an sp3 hybridized carbon, it can undergo a substitution reaction when reacted with a nucleophile, and that's actually shown right here, okay? So this is kind of the top part of the slide. Let's unpack this substitution, okay? So right here, let's unpack this just for a second. Come on, Apple Pencil, do your thing. There we go. All right, so if we take a look at this molecule right here, remember, X represents a halogen. And you know the halogens are more electronegative than carbon. And so therefore, that means there's going to be a dipole going this way, like that. So that means that this carbon, the one attached to the halogen, is going to be delta plus. So we have, if X is a chloride bromide, if X is equal to chlorine, bromine, or iodine, remember, those are all good leaving groups. Why? Because they're the conjugate bases of a strong acid. And so if they're good leaving groups, that means that we can simultaneously have a nucleophilic attack and a loss of leaving group occurring. Watch. So we're going to have our nucleophilic attack. It's going to attack the electrophilic carbon, and then we're going to lose our leaving group. And so we're substituting the halogen for the nucleophile. So that's why we call it a substitution reaction, okay? And this is actually an example of an SN2 reaction. So that just this particular example. Now below that, it says we have an elimination reaction, and you can imagine that in an elimination reaction, it's where we lose something. So it says below, it says alkyl halides can undergo an elimination reaction when reacted with a base. So let's imagine we have some kind of base. It could be something like sodium hydroxide, right? That's a strong base. But you notice that in the first example, we were dealing with a primary alkyl halide, and in the second one, we're dealing with a tertiary alkyl halide. So there's a big difference in reactivity between the two. And so if you can't figure out what's going on in this reaction, you see that you're forming an alkene here. So what that means is the base is actually removing a proton, right? Because this carbon initially had 1, 2, 3 protons, but now it's sp2 hybridized, so it only has 2. So what's happening is the base is taking one of the protons, the pair of electrons is making the pi bond, and you're losing your halide, chlorine, bromine, or iodine, as chloride, bromide, or iodide, as your leaving group. So we call that an elimination reaction, right? Because you're eliminating the conjugate acid of your base, technically. I guess it's not really that. You're eliminating the hydrogen and the halide from the compound. That would be a more accurate way of saying it. So what do nucleophiles and bases have in common? Well, oftentimes they're both negatively charged, right? You know, they're both negatively charged. And anyhow, so we're going to differentiate between nucleophiles and bases as we move throughout the chapter. But it says here, sometimes a reagent can act as a nucleophile or a base. And so we're going to get a mixture of elimination and substitution. They're actually going to compete. The two mechanisms will compete. So if we think about this compound here, this is called 2-chloropropane, or you could call it isopropyl chloride. Either one is totally fine. You can see that to get the substitution product, right, what happened is we substituted the hydroxide substituted or took the place of the chlorine, which became a chloride. So we get a nucleophilic attack and a loss of leaving group like that. And that gave us the substitution product. Now for the elimination, okay, we have a slightly different mechanism because now we have one of these protons. Now, if you're wondering, Mr. Dion, there's 3 protons here. Why are you just drawing one? I'm just drawing one for instructional purposes only, just because that I only need one to show what's happening, okay? So what's going to happen now is your hydroxide is going to behave as a base, right? And it's going to accept a proton. It's going to pick up this proton, form the double bond, and we lose our leaving group. And that would give you the elimination product, which we call propene. Now you see that it actually tells us on this slide that the elimination product in this particular reaction happens to be the major product, and the substitution product happens to be the minor product in this particular case. So, and it says here in the example above, which compound is the substrate? So the substrate, okay, the substrate is the alkyl halide. So we'll put here, it is the alkyl halide, which is this here, the isopropyl chloride. So just so you know, in this chapter and from now on in organic chemistry, you probably have heard the word substrate used in a biology class when you're talking about enzyme catalyzed reactions, right? You say the substrate binds to the binding site, you know, anyhow. But anyhow, in this class, when we talk about a substrate, it's usually just means a starting material, okay? Starting material, reactant, whatever you want to call it. Okay, but that's what a substrate means in organic chemistry. So substrate in this case is the reactant, the starting organic molecule. So why do substitution and elimination reactions occur? Well, I've tried to uncover that with you already, a little bit already, but it says here 2 main reasons why alkyl halides undergo substitution and elimination. The first one is if we look at that compound on the previous slide, right? Let me use my black pen here. If I draw that isopropyl chloride, this compound right here, you guys know that chlorine is more electronegative than carbon, so there's going to be a dipole going this way, which means that this carbon is going to be electrophilic. So of course a nucleophile can attack it. So The halogen is electron withdrawing, creates a partial positive carbon, a charge on the alpha carbon, making it susceptible to nucleophilic attack. So another thing you want to know is what an alpha carbon is, okay? An alpha carbon is the carbon attached to the halogen. So this carbon here, this would be the alpha carbon, right? This carbon right here, that would be the alpha carbon. So whenever I say alpha carbon, it's the one directly attached to the halogen. So it's the one that's susceptible to nucleophilic attack. Now, it says here the halogen acts as a leaving group, and for the substrate to undergo a substitution or elimination, it has to possess what we call a good leaving group. And I told you that a good leaving group is the conjugate base of a strong acid. So when did we learn strong acids? Well, you learned some in General Chemistry 1, but we've also talked about a few more in this class. And so that was covered in chapter 3 in the acids basis chapter. We said this is a strong acid or whatever. So whatever the conjugate base is of any strong acid, that's categorized as a good leaving group. So let's talk a little bit more about leaving groups. And here's the definition that I wrote down on the previous slide. Good leaving groups are nothing more than the conjugate base of a strong acid. What do we categorize as a strong acid? Okay, in this class, anything that has a pKa that is less than 0, we consider that to be a strong acid. So you can see our cutoff would be somewhere around here in this class, right? So everything below the blue line is an acid. So HF, H2O, ethanol, butanol, ammonia, right? Those all have pKa's that are greater than 0. So that's why fluoride is not a good leaving group, okay? Because it's the conjugate base of a weak acid. But if you look at a hydronium ion has a pKa of -2 approximately. What's its conjugate base? Its conjugate base is water. So is water a good leaving group? You bet your Bobby socks it is. This one here, this is called, I'll write down the name. This is called, let me use a finer tip pen. This is called toluene. It's got a long name. Toluene sulfonic acid. Okay, so this leaving group here, we have a shorter name. We call it a tosylate. So a tosylate is the conjugate base of toluene sulfonic acid, which is a strong acid. It has a pKa of -3. And so a tosylate is a good leaving group. Don't worry, you don't have to draw this whole thing every time. Usually we just write OTS. So we write O-TS, and we call that the tosylate. Then I also explained these in detail already this morning: chloride, bromide, and iodide. Right, those are the conjugate bases of hydrochloric acid, hydrobromic acid, hydroiodic acid, all of which are strong acids. And so, are they good leaving groups? Yes. So, can you memorize these? Sure, I guess you could, but I think an easier way to do it is to know what the strong acids are and just think about their conjugate bases. So, some instructors will say, well, a conjugate base is like me. They'll say a good leaving group is the conjugate base of a strong acid. That's the way I was taught it. That's the way I think about it. But another way you could think about it is good leaving groups are also, you could say they're also weak bases. Okay, a good leaving group is a weak base. A weak base, right? So these are all weak bases, whereas these are not weak bases. But again, I find it easier to just memorize the strong acids and say, well, is this the conjugate of a strong acid? Yep, then it's a good leaving group, end of story, okay? So if you see things like fluoride, hydroxide, alkoxides, remember NH2 minus, this is called an amide ion. So this is the amide ion. That is also a poor leaving group. Why? Because again, these are all the conjugate bases of weak acids. So there you go. Now that we've covered what a good leaving group is, let's talk a little bit more about alkyl halides, and let's talk about their nomenclature. So let's talk about nomenclature. How do you name an alkyl halide? Okay, we can't keep talking about them without you being able to identify them, by their name. So alkyl halides are compounds where the carbon group, again, an alkyl group, is bonded to a halide. Fluoride, chloride, bromide, or iodide. We learned the steps of how to name an alkene in chapter 4, part 4.2. We talked about finding the parent chain, right, the longest chain. We identified and we named the substituents. So if you have a fluorine That's called a fluoro, F-L-U, fluoro, okay? So I have people all the time that'll say it's fluoro. That I don't know what that is. Some kind of something you can buy at the grocery store, maybe. Anyhow, so chlorine would be a chloro. Okay, bromine is a bromo, and iodine is iodo. Okay, so those are the prefixes for the halogens. So you've got to know all the other substituents that we learned: methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. Then you give a locant to all of your substituents. So is it a 3-ethyl, 4-methyl, etc.? You put them together in alphabetical order. And if the halide group is the key substituent, don't really worry about this a whole lot, okay? But we're trying to find some halogens here. So let's take a look at these. For each of the examples, convince yourself that they're, I think this is a funny way of putting it, just convince yourself, and then you're good. That's not a good way to do science. But anyhow, all he's saying is that these are all numbered correctly. So just prove it to yourself. Well, this one here, 2-chloropropane, it wouldn't matter. You could start over here, 1, 2, 3, and you'd still end up with 2-chloropropane, right? Because there's symmetry in the molecule. But you also recognize this group here, this alkyl group, as being an isopropyl group. So you could also call this, I'll put it in blue, you could also call this isopropyl chloride. That it would also be an acceptable way of naming it. The next one, you can see, remember, we always want to give our substituents the first substituent the lowest possible number. So, of course, we're going to start numbering here on the left. So we have a 2-bromo, 2-methyl pentane. And the next one, you could practice your, if you want to get a little more practice on your stereochemistry, here the proton is going in the back like that. So we go from 1 to 2 to 3, and then 4 is this. So we go like that. Yeah, it looks good to me. So that's an R compound. And of course, we want to give the first substituent the lowest possible number. So the first substituent in this case happens to be this methyl group at carbon number 2. We have 2 more at carbon number 3, and then we have a bromo at carbon 5. But we put the bromo first in the name. Why? Because B comes before M in the alphabet. Remember, we ignore the prefix tri, right? So there we go. So that's a little bit on alkyl halide nomenclature, and I think we convinced ourselves on the numbering of these. But like I told you, you can also use common names for alkyl halides. They are perfectly acceptable by IUPAC. So when we say systematic and common, they're both accepted by IUPAC. There's nothing wrong with either of them. Okay, the systematic way is just find the longest carbon chain, right, and then use the prefixes and all that. So if you had this compound here, you'd call it what? Chloroethane. If you're wondering, why don't you call it 1-chloroethane? It's redundant, okay? The chlorine has to be attached to this carbon or this carbon. They would both be considered to be carbon number 1. It's not until you get to 3 carbons where you could have the chlorine here, rather, or you could have it here. So this would be 1-chloropropane, and this would be 2-chloropropane. But to give it the common name, all you do is you name the alkyl group. So again, alkyl groups: methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. And so I only expect you to know common names when we're dealing with alkyl groups that I've taught you, okay? You don't have to do it neopentyl bromide or something like that, some group that we didn't even cover. Don't worry about it. Now, at the bottom, we have dichloromethane, right? So we have 1 carbon, right, a CH2. So this is some kind of methane. We have 2 chlorines. We don't have to call it 1,1-dichloromethane. That's redundant because there's only 1 carbon anyway. And then the common name for that compound is methylene chloride. So remember that CH3, remember that's a methyl group, methyl. CH2, if you're talking about a CH2 group, the technical name, or the appropriate name, I should say, is a methylene. And if you're talking about a CH group, that's called a methyne, I-N-E, methyne, like that. So we call this methylene because it's got a methylene, and then we call it methylene chloride. So again, methylene chloride, as I told you earlier today, is widely used as a solvent in organic chemistry. However, it's being phased out. It's going to become essentially illegal. And like I told you, I've used this by, with a kiloton in industry, and we actually use it in the lab at UCCS sometimes. So we're going to have to find a way to do some experiments without using methylene chloride. Okay. It's used as a solvent. Like I said, it's used as a paint thinner, many different uses of methylene chloride. So let's see if we can give some names to these molecules here. So we have two alkyl halides. Boy, we get all kinds of stereocenters in these two, don't we? So let's see if we can come up with some names here. The first one has a stereocenter. So let's see here. So would this be an R stereocenter or an S stereocenter? Does anybody have an idea about this one? Would this be R or S? Yeah, I got R as well, Isaac, okay? So let me prove it to you. So if you're struggling with this, okay, here's how we're going to do this. The iodine is going to be number 1. The bromine will be number 2. The isopropyl is going to be number 3. So there's a couple of ways you could do this, okay? Because the methyl group is pointing down like this. It's not going in the back, okay? So one way you could do it is to put your eyeball up. Imagine your eyeball is up at the top like this, right? And what would you see? If you were looking down, you'd see the iodine, then you'd see the bromine, and then you'd see the isopropyl group like this. So you're going 1, 2, 3, like that. So that would be R. Okay, that's one way of doing it. Okay, that's one way of doing it. However, if you follow the rules that were covered in Chapter 5, the way it's usually taught to organic chemistry students is this. Remember that if you swap two groups so that you can put the lowest priority group, which is the methyl, so you can put it in the back, when you swap two groups, you reverse the stereochemistry, right? So let's redraw the molecule, and we're going to swap the bromine and the methyl group. So I'm just going to, son of a gun, where was I? I'm just going to scribble it up here. So we'll put it like this. We'll put the bromine going down. The iodine doesn't change. And then we'll put the methyl group in the back like this, okay? So now we're going to go from what did I do wrong here?